Hello, my name is Nourhan and I'm going to talk about our work BoosterNet. The aim of this work is to improve domain generalization of deep neural networks using culpability-ranked features. The remarkable success of deep neural networks is built on the IID assumption, where the training and the test datasets are assumed to have the same distribution. However, this assumption is commonly violated in real-life applications. We refer to the discrepancy between the training and the test data distributions as domain shift. With a domain shift, the performance of the models will be significantly degraded. Domain generalization is therefore proposed to enhance the generalization of a model on unseen out-of-distribution target data. Current domain generalization methods suffer from two main drawbacks. First, they strictly rely on the availability of many training domains, and they often require restructuring or changes in the network architecture or the learning paradigm across the different data. Well, it's more realistic to generalize from a single training domain without changing the network architecture or the learning paradigm of the base network. Given any of the shelf network, we call it here network A, trained with a single domain data, we propose BoosterNet, a lean add-on network that can be simply appended to any arbitrary network A to improve its generalization capability without requiring any of the changes. Inspired by shortcut training and the feature suppression, the idea here is to train BoosterNet with a number of culpable features extracted from network A in order to guide the learning behavior of BoosterNet, thus allowing it to generalize extremely effectively across out-of-distribution domains. To train BoosterNet first, we calculate the class-specific culpability score for each unit in network A using this novel culpability metric, which reflects the contribution of each unit towards wrong predictions for each class. Here, low scores identify units less culpable in generating errors for that specific class. Then we will sort out the units based on their scores in order to extract a number of discriminant and confusion features from each class, such that the discriminant features are coming from the least culpable units, while the confusion features are extracted from the units with the highest culpability scores. Once extracted, we will stack them to train BoosterNet with. So BoosterNet is learning from these class-wise discriminant and confusion features, which ended up with an improved performance and generalizability over the same task as compared to network A. Note that BoosterNet is also trained using episodic training, such that we divide the features into meta-train and meta-test to create different meta-tasks. At Inference, we have the test image and we need to extract the discriminant and confusion features from network A in order to feed BoosterNet with. Since we have different units assigned to different classes, we need to know which units to activate in network A. And for that, we propose using the Siamese network as a gating mechanism to trigger or activate the most probable class units. To do that, we train the Siamese network using a distance-based contrastive loss such that each class would have a unique embedding. Then we find the test image embedding using the same Siamese network, and we measure the distance between the test image embedding and all the other class-wise embeddings. The class associated with the smallest distance is then assigned as the most probable class of the test image, and the corresponding units of that class are activated to extract the test image, discriminant, and confusion features for final prediction by BoosterNet. To validate the performance of BoosterNet, we evaluate on the digits benchmark, where we used MNIST for training network A and the other datasets for testing, representing out-of-distribution target data. For network A, we tried different architectures, which are literature standards, including ResNet 18, ResNet 50, ResNet 152, and VGG16, and the results are shown in experiments A to D. We can see that the performance degrades remarkably on unseen out-of-distribution data, and it drops to below 10 in some cases. On the other hand, the performance of BoosterNet when appended to each of these networks is given in experiments E to H, and we can see that the performance is improved significantly. For example, compared to ResNet 50 alone, BoosterNet improved the performance by almost 42%. Similarly, we verified the performance of BoosterNet on the skin lesions classification task, where we trained on the Ham dataset and we tested on the other datasets representing out-of-distribution target data. We noticed similar improved behavior compared to core network A. For example, compared to ResNet 18, BoosterNet improved the performance by 21%. Please refer to our paper for more experiments. Thank you for listening.